Hi, thank you, Tegan. So our project is looking at the impact of extreme weather events on grassland ecosystem function. And today I'm going to focus on some of the results around the impact of flooding and pea mobilization. And as we know, with climate change, there's predicted much more frequent extreme events in the future, extreme weather events such as flooding and droughts. And this has been evidenced over the last successive winters in the UK with prolonged periods of flooding across many pastures and arable lands. So this is part of a larger project called Climate Smart Grasslands, which is aimed at generating strategies to safeguard grasslands against extreme weather events through resilience and building resilience in these systems. But we also need to try and understand how the grasslands respond to the extreme events and the impact of these on the plant, soil and microbe interactions. So the work we're doing at Bangor focuses on the impact mainly on whole ecosystem services, so not just on nutrient cycling, and whether we can identify a tipping point where the system will no longer function in the way it needs to following these events. And then there's also some work with our collaborators at Aberystwyth and CEH who are developing strategies to improve resistance and resilience in these grasslands. And in Aberystwyth, they're developing new hybrid grass species. So in terms of ecosystem services, I'm sure a lot of you have heard about all these terms, but today we're going to really just focus on those pertaining to phosphorus cycling, so nutrient cycling and water, so the impact on water quality. And I'm going to give a little bit of a background on some of the results we've had from a flooding experiment looking at the impact of flooding on the floodwater and soil solution chemistry, looking at the dissolved reactive P or molybdate reactive P and the unreactive P and the dissolved organic carbon, and then the impact on some of the soil chemical properties, so the extractable phosphorus, iron and aluminium after a flood event, and the redox potential during the flooding and after. And then also soil microbial biomass and community structure analysed by PLFAs, and just a little bit of an overview of some of the other indicators of the impacts on the grasslands, such as earthworms and the plant response. So we had a field plot experiment out at Bangor in North Wales, and we had 3 by 3 metre plots. Had 8 plots which we flooded and 8 which were left as a control. And we flooded these plots with water from the adjacent river back in April, and maintained the flood for 8 weeks. So we can see the flooding here with the grass submerged under the water for the whole period of that 8 weeks. And during that time we took soil moisture data and weekly redox measurements of the soil, and then took soil solution, flood water, and the water coming into the plots for chemistry analysis and greenhouse gas measurements, and also just did a bit of a visual assessment of the plant material and macrofaunal activity. So this is just a schematic showing our plots and some of the instrumentation that we have there. So we have some acclimators which are downloading some of the soil moisture and soil temperature on a 3-hourly basis. We have a plant monitoring area where we took a sample for biomass production following the flooding, and we'll take during recovery, and we'll also look at the nutrient quality and forage quality of that. We've got some macro horizons to take soil solution samples, gas chamber, an area where we take soil cores, and then also an area which we excavate to look at numbers of earthworms following the stress. And also we've buried some tea bags If you bury a certain type of tea bags, they've generated what they call the tea bag index, which can give you an idea of the rate of decomposition of organic matter based on how much weight difference there is between when you bury them and when you dig them up. So after the flood, we removed the floodwater, and then just before doing that, we took water samples and redox and greenhouse gas measurements. And then the same day, we excavated an area where we took soil samples for PLFA analysis and soil chemistry, and also sorted for earthworms, hand sorted for earthworms. So this just gives you some of the data of the water chemistry during the flooding period. So along the x-axis, we've got days since the start of the flooding, and here we have the dissolved reactive P in the soil solution, in the floodwater, and in the inlet water. So what was coming in, and we saw a peak right at the beginning of the flooding, so a pulse of P release into the soil solution at the beginning of the flooding. Some a little ways through, and then another peak further through again. And then there wasn't really that much difference between that and the inlet water. And with the dissolved unreactive P, so probably the organic P, we only really saw a significant difference between the inlet water and the soil solution right at the beginning, which maybe could be release of phosphorus from the microbial biomass following the start of the flooding period and the wetting of the soils. So when we looked at the DRP compared to the redox, we saw that we got one of our peaks of P release during the period when it went anoxic. So maybe that was due to the release of P from iron and aluminium oxides and the reductive dissolution of those. When we also looked at the recovery period, and we also saw a peak of organic P or dissolved unreactive P immediately following the removal of the floodwater, which we didn't see in the dissolved molybdate reactive P. And if we looked at that compared to the dissolved organic carbon, we got an increase in our dissolved organic carbon here, and this is when we got an increase in our redox potential, and we quickly went up to aerobic conditions. So maybe it was the stimulation of the microbial community again, cycling some of the organic material that had been released. After the flood, when we looked at the soil nutrients as extractable nutrients, this was an acetic acid extract, an ICP, we found a significant reduction in our P in the flooded soils compared to the control soils, and also an increase in the iron and the aluminium. So that suggests that maybe we were mobilizing some of those iron P oxides. Looking at the soil microbiology, we saw a significant decrease in the total number of PLFAs following flooding, but we also saw a bit of a shift in the community structure. So these open squares and triangles show the control plots, where the circles and the black circles show the flooded plots. And there was an increase in the gram-negative bacteria in the flood plots and a decrease in the Actinomycetes. But we're not really sure what implications that has for P cycling. It needs to be investigated much further. In terms of other indicators, we had a large amount of plant die-off during the period, so that's a picture straight after the floodwater was removed. So pretty much all of the grass had died. But the recovery was quite quick, and after 4 weeks, which is this picture, we had 45% cover across the plots, an average of 45%. But when we looked at the plant species, there were many more species in these flooded plots, but a very low abundance of them. We think there's probably a lot of weed species. And there also seemed to be a shift in the dominant species. Whether that remains or not is to be seen, but we didn't really have much of the same pasture species, the ryegrass, which was dominant in the control plots. And we don't know at the moment what the plant forage analysis is going to show us, but we have sent those off to see whether this will have impacts for the nutrition. Really interesting was the earthworms, and we saw really low numbers of mature earthworms in all the plots, but much higher numbers of juveniles in the flooded plots compared to the control plots, and it was almost as if they hatched as soon as we took the water away. Some of them were still attached to the cocoons. So in terms of conclusions, we didn't really see a huge amount of phosphorus indications, but there was some indication of P release during the flooding, maybe linked to redox potential and dissolved organic carbon, and a significant reduction in extractable P with loss of P indicated. But it's possible that we missed a lot of this because of timing of taking of the samples, only taking them on a static weekly period. So in terms of further work, I'd like to look at the speciation in the post-flood soils of both the iron, inorganic and organic P fractions, and any input into the best ways to do that would be great. Also want to look at some controlled experiments, the partitioning of P within the soil, the plants, both the roots and the shoots, the microbial biomass, and the release patterns, maybe through use of isotopes. And previous work have indicated a large pulse of phosphorus release from the plants following die-off during the flood. So it will be good to look at some of that. We're also going to keep monitoring the recovery for pretty much the whole year to look at whether look at the shifts that we've seen in the microbial and plant communities persist. And this slide, I don't really have that much time to go into. It just gives an idea of some of the past work we've done, which has shown the release of P from the plant communities. So this is soil which was labelled with 33P 2 weeks before flooding. We had a treatment where there was only soil, one with soil and grass, and one with only grass. And these treatments here, T2 and T3, which had the grass, had much more P release in the floodwater than just the soil. And the P33 data suggests that the grass took the P up during incubation and then released it on decomposition during flooding. So I just need to acknowledge our funders, the NRN, the National Research Network in Wales, which is funded by Welsh Government. Thank you. Any questions?